Okay, well, welcome all of you students to, I guess, what is the 9th lecture in the quantum condensed matter physics course with neutrons. And hopefully we're being joined by several other students from all over the place. I'm going to ask you to do something a little different. I would like to know if there actually are people out there in internet land. So I would like one person from each location to please just type a hello with your location so we can see who is actually here. While we're waiting to hear that, my name's Stephen Nagler. My usual day job is I direct what's called the Quantum Condensed Matter Division at the Oak Ridge National Laboratory. As you might guess, we're people who do research in quantum condensed matter, but we are part of the Neutron Sciences Directorate, and as such, our major technique is neutron scattering. Okay, so I typically would be giving a lecture more similar to the last several that you've heard. In other words, more related to actual condensed matter physics. And I've noted the previous few lectures were somewhat theoretical. Today is possibly going to be a bit of comic relief. I'm going to concentrate on some experimental aspects and some instrumental aspects. Okay. Now it turns out I was for many years actually a professor at University of Florida in Gainesville, which is not too popular here in Knoxville, but I am actually a legitimate faculty member at the University of Tennessee in the SIRE program. I also am of the age where my arms are getting shorter or something, so I have to use these reading glasses. So I see that there's somebody here at least from San Diego, so we are, at the very least, we're reaching the West Coast. So thank you. So today I will talk about neutron instrumentation, preliminaries, and we'll get to a certain position here. I'm not going to yet maximize this PowerPoint file because there are a couple things I want to show you as we go along. First of all, why are we doing this here? Why do we have this quantum condensed matter division at ORNL? Well, it's because we have neutron sources. Most of you probably already know this, but we'll be talking a little bit today about how these sources work. So first, here's a picture of the Spallation neutron source. And this actually is a picture from some time ago when it was under construction. You can see, for those of you in Tennessee, this is missing, or it's just got under construction, the GINS building, which is the Joint Institute for Neutron Science, joint between University of Tennessee and Oak Ridge. And somewhere over here, there's a pit that currently, if you visit Oak Ridge, is actually the hotel where you'll stay or the visitor center. Okay. Now I'm going to get back later to a schematic that explains what these various parts are, but I will tell you that this is our central lab office building here, which actually consists of two back-to-back bananas, although the back part, or half of the back part of one of the bananas, is actually the Center for Nanophase Materials Sciences. And we have a bridge over to this building, which is the target building. The target building is where the neutrons are made and where all of the interesting action happens. It's a little bit hard to get the right perspective in this kind of picture because actually this building has an enormous volume inside. It's about the same volume as Neyland Stadium, which is a couple of blocks from here and holds 100,000 people. In this case, the target building, instead of holding a lot of people, it holds a lot of shielding and somewhere between 18 and 24 neutron scattering instruments. So it is currently the world's most intense pulsed spallation source of neutrons. And a few miles away down the hill, we also have the high flux isotope reactor. This is in an area called Milton Hill Valley. This is the reactor here. Now you'll notice SNS was sleek and curved and modern, and this is kind of old and boxy. SNS was built just a few years ago. It was about a 10-year construction project. The HIFER was built back in the 1960s. And it kind of looks like it, although it does have a new guide hall. And it's actually a high flux reactor. Originally, as you can guess from the name, the high flux isotope reactor, it was built primarily to produce isotopes, but over the years, it was a multi-purpose facility where neutron scattering became more and more important. And it has very intense continuous beams of neutrons. Now, should you ever visit Oak Ridge as a user, I'm not sure if this is the sunrise or the sunset, but I assume you'll get to know both of them well if you're a graduate student. So without further ado, let me move on and say a little bit about what I'm going to talk about. Okay. So first of all, in a moment, I'm going to tell you about some other resources where you can get more information. I'm being asked to talk about instrumentation. Okay, now instrumentation is a vast subject when it comes to neutrons. It's not just the instruments that we use to do the experiments. I'm also going to talk about sources and how we shape neutron pulses or neutron spectra and how we transport neutrons. We could easily have a full course on this on its own. And it's the kind of thing that typically hasn't really been taught in detail in full courses, but there are some good resources on the web. There are some decent books. They're a little different than the books that were given in the syllabus for this course, so I'll point out a few of those. Okay, and then I'll go in some kind of crude order. We'll talk a little bit about how we make the neutrons that we need to use, okay, and how we detect the neutrons, because making the neutrons and measuring them is no good unless we actually detect them. I'll talk a little bit about how we transport neutrons, get them from A to B. Some about optical elements that we use to make the monochromatic neutron beams, often that we want monochromators, collimators, a little bit about shielding, a little bit about neutron filters, not necessarily today. I probably won't actually say anything, or certainly not much, about polarizers, because I know that Roger Pinn is going to give a couple of detailed lectures about polarized neutrons, and I assume that he'll cover that. And then finally, I'll say something about diffraction or elastic scattering, which actually these are not completely synonymous, okay, as we'll discuss, but they are quite related. And today I'm going to talk about powder diffractometers, continuous versus time of flight neutron sources, how they operate somewhat differently. I think it's a good, simple instrument that illustrates some of the basic principles of one versus the other. And I'll also talk a little bit about small angle scattering. I don't expect that we will get to inelastic scattering today. We'll look in some depth at inelastic scattering, and I'll also give you a bit of a tour around the instruments at SNS. Let's start by talking about some of the available resources that you might be able to use if you want to get more information. So first of all, there are now a few reasonably modern books out that have some of this information in a nice form. Now, there should be some svelte model up here illustrating these books, but since we're a graduate class in physics and material science, you don't have that. But here's the first book. If you look in the presenter box here, this is called Experimental Neutron Scattering. It's by Willis and Carlisle. It has sort of a quite broad coverage of some of the things that I'll be discussing here at a relatively introductory level. I think it's actually quite a nice book, and you can definitely find this right now at Amazon, and I don't know if you can find it used at ABE Books, but you might be able to. It's at least worth looking at. Now, I will say all of these books have their own peculiarities, and whereas I think all of the books I'm about to show you are good books, I have found in all books there are some things that not everybody will agree with, or there are little mistakes here and there, but basically these are pretty trustworthy and pretty good. The second book, which you can also find at Amazon or used, is called Neutron Scattering with the Triple Axis Spectrometer. And it's by a group of people from Brookhaven, Gan Shirani, Steve Shapiro, John Tranquata. It's got a lot of detailed information about neutron scattering in general and triple axis spectrometers in particular, based on their years of experience at Brookhaven National Laboratory. If you go and read some of the reviews of this book, you'll find that people from some other laboratories, especially overseas, critique it a little because they found it too Brookhaven-centric, but nevertheless, I think there's a lot of very good, basic, and important information in this book. It doesn't cover everything. It doesn't cover some of the newer innovations that have been made at ILL, but what's in here is accurate, good information, and it has a lot of things that if you actually choose to use neutrons are very helpful to know and not discussed in too many other places. Now, very recently, here's a new book that's by Heitman and Montroy from Missouri, and it's called Practical Neutron Scattering at a Steady State Source. Okay, there we go. Sorry, that's a little unfocused. Now, this book was produced as basically an outcome of a graduate course that was taught at Missouri and funded by an NSF grant for graduate education, research, and training called an IGERT. And Missouri has a research reactor. They have their own instruments. This is based on the author's experience with those instruments and with other places. Walter Montroy actually has worked at both pulse and continuous sources. And actually, this book is available in PDF form for free if you go to Walter Montroy's website. So the price is absolutely right. They've also essentially put it in the public domain and said, please use parts of this book for illustrative purposes. So I have felt free to borrow liberally for some of their diagrams. And I will also say that, well, I think the book is pretty good. I found a couple of little errors in there, but nothing that should concern you unduly. One of them happens to be in an exercise, so you may have to trust your instincts or ask questions if you decide to do them. But basically, I found it pretty good. Now, another thing that you can get to, many of you may be aware that there's a national school on X-ray and neutron scattering taught every summer, part at Argonne and these days part at Oak Ridge. And the notes, lectures, etc. from that summer school are put online every year, and you can go look at those, no charge. Okay, so they tend to be a little more experimentally oriented and a little broader than the lectures you've seen so far in this course, but they are also a pretty good source of information. And I've actually borrowed some pictures from and a couple of slides from some of the lectures there, notably Jack Carpenter, one or two from Bruce Golan, and I've also borrowed a few, at least, images from Ian Anderson, who was my colleague at SNS, okay, and was the director actually for many years. Okay, let's see. All right, other places to get info. So pretty much every neutron source where you can do experiments has information about their instruments, right? And a lot of this stuff you just have to go out and find for yourself. Now what I have listed here is by no means complete, but it does list the major sources in the US and some sources in Europe. So if you go to neutrons.ornl.gov, you can find all kinds of information about instruments at HIFER and SNS. I'm actually going to talk about a fair number of those probably on Thursday, but you can find more detail there. NIST is in Gaithersburg, Maryland, near Washington, D.C., operates a Center for Neutron Research that has an outstanding track record, a lot of users, and they have a lot of excellent information there at their website, including some great information on small angle scattering, among other things. And there's a Neutron Scattering Center, a pulse source at Los Alamos, the Lujan Center, which also has its website listing its instruments. I haven't listed the Canadian Neutron Beam Center, but I think you'll be able to find that, and they have some nice instruments there as well. That's up in Chalk River, Ontario. Now, from overseas, I've listed a few different things here. Now, I want to point out, let's see if I can get my pointer. This is both a reactor and a spallation source. Reactor, spallation source. The spallation sources are pulsed in this case. The reactor is continuous. The ILL, Institut L'Oreal-Langevin in Grenoble, France, has probably one of the most comprehensive lists of instruments and information that you'll find anywhere for reactor-based sources. They used to publish something called a yellow book. Right now, I think pretty much all of the information that was in the yellow book is available on the web, and you can plunge there into great detail. And sort of the pulse source that has operated consistently for the last several years in Europe, producing great results, is at the Rutherford Labs in England. It's the ISIS pulse neutron source. There you can find a lot about pulsed instruments. FRM2 is the research reactor in Munich that is built relatively recently, which is very unusual for reactors. And so they've got a lot of advanced instrumentation concepts that they've put into practice based on years of experience at ILL and elsewhere. Quite interesting to look at. SynQ is at the Paul Scherrer Institute in Switzerland. Now, it actually is a spallation source, but it's a continuous source of neutrons. Okay, in the lectures that I'm about to give you, I will assume that accelerator-based spallation sources are pulsed and reactors are continuous, but it doesn't have to be that way. So if you're interested in sources, it would be good to take a look at that. J-Park in Japan is another next-generation spallation source. Amazingly, they were knocked out of operation by Fukushima. Sorry, not by Fukushima, by the the events that led to Fukushima, the hurricane or the earthquake rather, and the tsunami. And for a while they were down, but they managed to recover in very short order, and they're operating again, which is kind of spectacular. And that's one of the more advanced sources in the world. And for something completely different, the Frank Laboratory, which is in Russia, is actually a pulsed reactor. Okay, so it's possible to have a pulsed reactor as well. Now, there are several other sources in the world that one can think of that have good information, including ANSTO in Australia, Saclay in France, the HCB in Germany, and Jülich in Germany, but I think this is more than enough to get you started. So if you would like some extra information above and beyond what we'll cover here, which is really going to be somewhat cursory, there are some sources that you can tap. Okay, now I think we'll go to the full screen, and I'll stop and ask if there are any questions about what I've said so far. Okay. Well, here, I'm sure everybody here has probably seen this before, but it's always a nice image to look at. Right, this is the poster that was produced by the Nobel Organization in 1994, when they essentially honored the field of neutron scattering by giving the Nobel Prize jointly to Clifford Scholl, who along with Ernie Wolin pioneered neutron diffraction here at Oak Ridge, and Bert Brockhaus, who at Chalk River in Canada pioneered inelastic scattering. And you know, this poster in a nutshell captures a lot of what's good about neutron scattering, and it also has sort of basically what happens in an experiment, showing in a sense a neutron source, a collimated beam, a monochromated beam, scattered from a sample finally into a detector, sort of schematically illustrating the triple axis spectrometer that Brockhaus invented. If you haven't looked at this live in color, full size, I urge you to do so. And by the way, I believe this is still true. If you're interested in any of the Nobel Prizes, you can write away to the Nobel Foundation, and they'll send you these posters for free until they run out of them, which is kind of a nice deal if you like sort of big scientific, nerdy posters. But some of them are quite informative. Okay, well, here's a slide that got messed up in the transition from one computer to another, but it just reminds you, what is the basic experiment we're doing in neutron scattering? Okay, so what we do is we want to take a beam of neutrons where we know the initial momentum, Ki, which is a vector, right? The initial energy, E sub I, not a vector. Okay, thank you. Possibly prepare it in a known spin state, or maybe not. Okay, and we scatter it off of the material we wish to learn about, and we look at a beam that has a known final momentum, a known final energy, and perhaps a known final spin state. And the independent variables that we measure are the momentum transfer, Q, which is a vector, it's Ki minus Kf, and these, what look like Greek letter mu's, are supposed to be vector signs, which they are, in fact, on my computer, but not on this one. So my apologies for that. And I'm also, since this course starts with quantum, h bar is equal to 1 if it doesn't appear, so you'll have to imagine it's there. we have an energy transfer, h bar omega, or in this case just omega, which is EI minus EF. So these are just conservation of energy and momentum. And what we are measuring when we do this, ultimately, is neutrons that are scattered into a detector. Okay? And we can relate these back to the properties of the material. But in order to do that, we have to take account of various things. For example, there's an intrinsic quantity that we want to measure, but we don't measure it in the raw. We measure it convolved with a sort of resolution function because the instrument doesn't measure things perfectly. Right? We define a scattering angle, but there's actually some uncertainty in the scattering angle. We define these incident and scattered momentums and energies, but there's some uncertainty in those. Okay? In addition, the counters just count whatever neutrons reach them. Okay? They don't care if they're the neutrons that we plan to count. So we have other neutrons that hit the detector. These are background. Right? That messes up the measurement. These are things we have to minimize, right? The background. We want to see the signal. Okay, so there are a lot of considerations that go into it. And neutrons are very, very weak scatterers. Okay, now, when I say they're very weak scatterers, I'm going to illustrate it with something. So now I'm going to, let's see. All right. Never mind that. That's something everybody knows. I'm going to illustrate, in a sense, something about more or less the scattering strength of neutrons. And let's see here. Whoa. I guess that's a smart notebook. Okay. So I'm going to do the following thought exercise, and this is audience participation. Okay. We all know that when we scatter neutrons, we measure the strength of scattering in a cross-section, which is something that has the units of area. This is something you've covered, right? There's an interaction that is linear in a scattering length b, so the cross-section goes something like b squared. So let's imagine that I do the following exercise. I take a fake crystal, which I'm going to say is diamond, but let's see here. Okay. I make a simple cubic lattice of diamond atoms, right? So if I look at it edge on, these are just supposed to be sitting on a square. Sorry, these are carbon atoms. So it's simple cubic lattice, and let me make it the same density as diamond. And if you look up in a scattering table, you'll find that carbon scatters neutrons reasonably strongly. Okay. So now let's pretend that each of these carbon atoms is actually a basketball, right? And I'm now going to scatter neutrons, and the neutron that's going to scatter is a tennis ball. Okay, so I throw a tennis ball at a bunch of basketballs, and I want to normalize the cross-section so that the probability that this tennis ball is going to scatter off the basketballs is the same as the probability that a neutron is going to scatter off a carbon atom. Okay? And so in order to do that, I basically have to find the right area per carbon atom, right? And I have to imagine how much of that is filled with carbon and how much is empty space. And so from that, you roughly know what a basketball is, right? Basketball's 10 centimeters or something. I want to find the lattice constant A that would normalize this correctly. So in other words, I throw a neutron at this and it scatters. So I'm going to ask for guesses. Anybody remotely, feel free to type in your guess. You can guess in meters or any other unit, any local guesses. What does this lattice constant have to be? That's a pretty good guess, not terribly metric. Turns out it's about 3 miles, and that's about right, okay? So that is really, it shows you just how weak neutron scattering really is. Now, in a real crystal, of course, the fact that you probably have 10 to the 8th layers, means that the scattering probability is not 0. Nevertheless, if I compare the scattering strength to photons that are scattering off of something that has an electromagnetic charge distribution, or to electrons which are actually charged themselves, right? Actually, I think it's more like probably about 3 kilometers, but you can see that this is an enormous difference. So basically, we have to use every neutron to its fullest advantage, or try and squeeze out as much as we can and get it on the sample. All right? And we have to reject those neutrons that are not contributing to our signal. Okay, so in that sense, neutron scattering, it's a flux-limited technique because the scattering is so weak that we really need to get strong sources and as much as we can possibly get onto the sample. Okay, so we'll keep that in mind. Okay, so the next thing is how do these experiments actually work? Well, first of all, right, I have some source of neutrons. Okay, what that source is, we will worry about later, but the source, one characteristic of it, is that it is a 4 pi source, right? Neutrons are coming out in all directions. Hopefully everybody understands what I mean by a 4 pi source. So this is similar to a candle. Okay? It's not like a laser, or if I manufacture X-rays using synchrotron radiation, thanks Wei, I have a source that has built-in directionality. Not so with this neutron source. Okay, unless I do something to reject the neutrons that are not going in the direction that I want. So the first thing is I have a source. Now that source emanates neutrons in all directions. Now, depending how we make the neutrons that come out are not neutrons that have the right wavelength for the experiments that we want to do, or the right energies or the right velocities. The way I make neutrons, typically, these neutrons are too fast, too energetic, the wavelengths are too short, right? So I need to change the spectrum so that it becomes something useful, right? So in all cases, I do something that the neutrons pass through which moderates the neutrons. Now, this was something that was first explored by Enrico Fermi in the 1930s, sometime shortly after neutrons were discovered. And he basically found out that, if neutrons were hitting wood, they would behave differently in inducing nuclear reactions as opposed to when they are, hitting a piece of metal or something. And ultimately, he figured out that what's going on is wood or other things that tend to have a lot of hydrogen in them, right? When a neutron comes and hits that, it causes the hydrogen atom to recoil, it loses a little bit of energy, bounces around, and the net result is that some of the neutron's kinetic energy is transmitted to this hydrogen or whatever, and the spectrum that comes out, ultimately, if I do this completely, comes into thermal equilibrium more or less with this moderator. At least this is the case in a reactor, close to it, and it comes out with a different spectrum. Okay, now the point is, when this neutron comes in here and bounces around all over the place, from any point here, I also have, unless I do something about it, another 4 pi source of neutrons. So I have neutrons, again, coming out all over the place in all directions in any way I look. Of course, now I hope that these neutrons have sort of the right spectrum. But a 4 pi source of neutrons doesn't help me too much if I want to do a scattering experiment where I know the incident momentum, right? So I now have to extract the neutrons that are going to be useful, which have some more directionality. So I do this by some kind of extraction method, and this might be, say, a beam tube. Okay, so in some neutron sources, we just stick a tube in there. There's material all around that absorbs those neutrons that we don't want, right? So we'll shield that also. So this is shielding, right? So I only have neutrons coming on the beam tube. Now I might want to shape the angular distribution of those neutrons, right? So in order to do that, I may put into this beam tube some additional collimation, right? That now helps define neutrons that come out with a much narrower sort of angular distribution. And in fact, I may also wish to transport those neutrons far away from the source so that I either have more room to build an instrument, as we'll see, or I can get them away from an area of high background, or I can shape the spectrum a little further, and in that case we use some optics, that we call neutron guides. Okay. Well, let's see. You'll have to forgive my writing and my efforts to use this smartboard. There we go. So we have guides. Now you may have guides, you may not have guides, but it's something that we could have. And it's only at this point that finally I now have a beam of neutrons that I can do something with, right? It's still not a monochromatic beam. If I happen to need a monochromatic beam, I have to do something further. I have to use some kind of method so that I know what is the incident momentum, incident energy, right? So the typical thing, I'm going to now assume that this is coming from a reactor source. And let's see, I need to go back to this, and let's get another one of these out. Right, so now I have these neutrons coming out, and maybe they'll bounce off of a monochromator crystal and now come out primarily monochromatic, right? So at this point, I now have some kind of distribution. How about, let's use a scalar energy. That always works better in my experience. I now have some kind of actual fairly monochromatic beam, but you'll notice that I have a delta K and a delta E. Right, now I can scatter this beam off the sample. Right, that's the thing I want to investigate. And okay, so now I have a KF and an EF. And sometimes I need to define this, I probably need to analyze it, but I'm not going to draw that. I'll just go to the last point, eventually. I'm not going to draw a full triple axis, but I have to do something to actually count these neutrons. Right? I have a detector. Now, the other thing is the detector sees any neutron that comes to it. Okay? It sees neutrons from the source. It sees neutrons from the sky. Okay? It sees neutrons from bouncing off the walls. So these detectors typically have to be shielded quite heavily. Okay, so all the considerations that go into this, that's what we're going to try and talk about in a little more detail. Now, let me make one, I'll save this other point for later. So I'm going to move now from this whiteboard back, hopefully, to a PowerPoint file. Okay. All right, so all of this goes into this scattering experiment. And you can see I've differentiated here between elastic and inelastic scattering. And we're going to now work our way through and see what we need to do to get there. Okay, the first thing I'd like to do, though, is I want to show you just a few unit conversions. Okay? So first of all, typically these days we talk about neutron energies in the thermal range in milli-electron volts. But if you go through the literature and some of the references I've given you or some of the other ones, you'll see people using terahertz. Right, a terahertz is about 4 milli-electron volts. Not too many are using inverse picoseconds, but you will see it. People tend to use wave numbers, especially infrared type people. So 1 terahertz is 33 wave numbers, or a millivolt is 8 wave numbers. Quite often we talk about energies in terms of temperature. It's really Boltzmann's constant times temperature. So a millivolt is about 11 or 12 Kelvin. And neutrons being magnetic, you can see that if I have one Bohr magneton, right? I can have one Bohr magnetron in 1 Tesla, and that's about a little less than 0.06 millielectron volts. So these are typically the units that people use when we discuss neutrons and neutron scattering. This is a useful table. And keep in mind, neutrons are massive particles, so they have an energy 1/2 mv squared. Okay, they have a de Broglie wavelength, right? The momentum h bar k can be related to the wavelength lambda. And if I use units of millivolts for E and angstroms for wavelength, I find that E is about 81 or 82 divided by lambda squared. Okay. So converting this into velocities, you'll find that the neutrons in the range that we're using typically are moving at thousands of meters per second. But of course, low energy neutrons can move more slowly. High energy neutrons can move more quickly. These are things that we sort of have to keep in mind. The neutrons that are in this general regime, tens of millielectron volts or so, have the right wavelengths that correspond to a few angstroms distances between atoms in a crystal. Okay, now, so let me go on now and talk a bit about sources, and we'll get back later to the experiment itself. So the first thing is we have two basic types of sources that I'm going to cover here. One is reactors, the other is the spallation source. Okay, a reactor is just a sustained chain reaction of fission events. Okay. We'll talk a little bit in more detail about it later. After neutrons were discovered, it took from 1932 until about 1942 before people actually produced chain reacting piles. Chicago Pile 1, the famous football stadium in Chicago, pioneered by Fermi, was the first one, okay, where people actually used the fission of uranium to produce neutrons. Now, basically, since then, we've had nuclear reactors that operate in roughly the same fashion. Right? We have a fission event. We generate, when we split whatever the fissioning nucleus is, more than one neutron. We also generate heat. Some of those neutrons go on and induce other fissions, and the whole thing just keeps on going. Okay? Now, one of the technical limitations that you run into is the amount of heat generated per useful neutron, or the amount of energy generated per useful neutron. So it turns out that for fission, this number is a couple of hundred capital M mega electron volts per neutron. Okay. Ultimately, what that means is if I want to make a very intense source of neutrons, which for our purposes you tend to want to have compact, there's a limit that you get to just from this heat that you have to extract. Okay. The second method that is now commonly used to make neutrons is spallation. Okay, where this comes from, the word to spall, if I hit a piece of rock or something with a hammer and a chip flies off, that's called spalling. It's possible to take a very energetic particle, smack it into a relatively heavy nucleus. This nucleus doesn't have to be something that's going to fission or whatever, but through a sort of complicated set of events that I'm not going to describe in detail, but you can read in any of these books, the nucleus will become excited, and when it finishes being excited, it will emit neutrons. And the amount of heat that it emits per neutron is more like 20 to 40 mega electron volts. So in fact, extracting the heat from a spallation source in principle is easier. Okay? As time evolved, when people first became aware of this, there were some proposals to build spallation sources that would be continuous sources of neutrons, much more intense than any reactor. Okay, there was a project called the Intense Neutron Generator proposed in Canada back in the 1960s. It never was built owing to cost and various practical technical difficulties. But eventually people realized that there was some advantage in actually having pulsed neutron sources. Okay, so those are what we're going to talk about as we move on here. Okay, well, let's first talk a little more detail about a reactor. I think probably most people here are familiar with this. Here's a basic cutout of a 0th order so-called swimming pool reactor. Okay, in this reactor we have some kind of fuel, which is uranium or maybe some form of uranium oxide of some type. Okay, and it's surrounded with water. Some of the water is there to cool. Some of the water is there to slow down the neutrons. Okay, when the neutrons are slowed down or moderated, right, the probability of fission is much greater. We have some method of controlling this, which typically involves sort of insertion or removal of some neutron absorbing material. Okay, and basically what ends up happening in this case is we get a great big gas bottle filled with neutrons, a large part of which are in thermal equilibrium with this moderating material. So if I have water at room temperature, which is about 300 Kelvin, right, I have a typical energy of about 30 millielectron volts. And if I poke a hole in the side of this gas bottle, the spectrum that comes out has a distribution of velocities that's the same as if I have a bottle full of gas and I poke a hole in that and I let it effuse out. Okay, and so this is a sort of a broad distribution, which I'm sure you're all familiar with. Here's a little more detail about this. If I use, and this is a particular example of uranium-235. Okay, if I hit that with a neutron, I produce 2 or 3 neutrons on average. One of those has to go on and cause another fission. Sometimes the neutron is absorbed, but on average, this will allow 1 neutron to escape. Okay, and you can see sort of down here, if I have a typical 20 megawatt research reactor, I have something like 10 to the 17th fissions per second. And the entire reactor volume, it sort of shows here, you get about 10 to the 18th neutrons, but for our purposes, right, what's interesting is the flux, because we want to take a small, this is a 4 pi source, right, going in all directions. We want to take a little slice of that with collimated neutrons. So we end up with fluxes in the center that are much, much less than this by some factor. Typical flux in the center of one of these sources would be 10 to the 14th or 10 to the 15th neutrons per square centimeter per second for a very intense neutron source. And we go downward from there as we monochromate or whatever. Okay, now the neutrons that are slowed down by moderation in a regular swimming pool reactor, you just have water and they're thermal, they're at whatever room temperature is, but we sometimes want to shape the spectrum further. So typically we would use some other hydrogenous material at a different temperature. So for example, here's a picture of a neutron moderator that's sitting in the reactor Opal, which is used in ANSTO in Australia. It's a fairly new reactor. And you can see that what this is basically, it's a cold source that uses deuterium that's cooled down to something, I guess, on the order of 20 Kelvin or so. Okay, so how the deuterium is cooled, well, it's some kind of helium refrigeration method, but the neutrons that bounce around in this source, which will now become its own 4 pi source, right, they are slowed down and they have a different spectrum, a different Maxwellian spectrum. Here's a cutout of the high flux isotope reactor at Oak Ridge. Okay, so this shows you a side view, and in here is the fuel element, okay, and the control mechanism. And this isn't a good enough picture to see that in detail, but this entire assembly is about the size of a typical garbage can. Okay, if I can find something, a large wastebasket, more or less, and I over here see a cutaway view, and you can see there's a core where the fuel is. Okay. It is surrounded by a reflector made of beryllium that bounces neutrons back in towards the core and keeps the flux in the center very high. And finally, there are some penetrations, and those penetrations are beam tubes. One of those beam tubes, which is near the core, actually contains a cold source, in this case, this cold source is supercritical hydrogen that's cooled down. Okay? So here's a question to think about. When this was being constructed, I was asked by an engineer, why do you put the cold source in there? It's very challenging in the center of the reactor. Why don't you bring the neutrons down the beam tube and put the cold source out here? Why not put the cold source way out here on the floor, and then you would just be cooling the neutrons that are going to the sample? Okay, does anybody know the answer to that? If you're at a remote location, you can just type yes or no. Well, the reason is that cold source is its own 4 pi source of neutrons. Right? So if I take these neutrons from here down one of these tubes, okay, I'm not collecting the full spectrum. I'm collecting some small slice that has a limited amount of angular divergence, right? That's basically, it's the ratio between, the area of this guy and the area of the source will give you some idea of the solid angle. Then I'm going to have a moderator stuck out there, and that's going to, again, send everything out in 4 pi, and it's going to reduce the intensity by at least that same factor, right? So you really can't pull that trick, right? So that's the thing to remember. Every time some neutron is hitting something that's going to scatter it incoherently, whether it's a moderator or something else, it makes a 4 pi source. Okay. Now, there's another aspect of this that I'll point out. Of these beam tubes in HYFER, there are 4 beam tubes. You can see that 3 of them actually don't look directly at the center, although one of them does look directly at the center. Okay, so those are called tangential beam tubes. This is called a radial beam tube. There's a reason for that, which I will get to in a minute. Okay. Now, here's sort of a graph that shows neutron flux versus, in this case, speed, but you can replace speed by changing the shape of this with the right Jacobian into energy or wavelength or whatever you want. Basically showing the difference between moderators at 2 different temperatures, right? 2 different Maxwellian distributions. So you can see for 300 Kelvin, right, if the neutrons are moderated there, I have a fairly broad distribution that covers this range of a few thousand meters per second. In energy, we'll see the graph below, and I'll come to that in a minute. Okay, I will also, if I cool this down and moderate it to a temperature more like 10 Kelvin, I dramatically shift that distribution to lower velocities, lower energies, and concomitantly longer wavelengths. Okay, so typically I need to think about, when I'm doing a neutron scattering experiment, what wavelength and energy of neutrons I most want to use, and it helps to have the instrument being illuminated by a beam tube that sees the correct moderator, okay, with the correct distribution of neutrons for that experiment. Now, this actually isn't the whole story. Okay, when I produce neutrons through fission, the neutron energies are in megavolts, not in millivolts. Not all of those neutrons are moderated. And if I look at the entire spectrum, these are the, these are the thermalized, these are the thermalized neutrons down here. Now I'm plotting this as a function of energy, and it's a logarithmic scale here. So that's 1 millielectron volt down here. That's an electron volt, right? And this, you can imagine, is sort of also logarithmic. So here's, this distribution is down here. I have a tail of neutrons of higher energies that are beyond thermal that I call epithermal. And I also have a pile of neutrons that aren't moderated at all, that are fast neutrons. Okay. So if you think about it, all of these are going to be there at the center in the core. And if I look straight at the core, I'm going to get all of these much higher energy neutrons going right down, the same as the thermalized neutrons. Okay. But if I look away from the core, I'm going to drastically sort of reduce this. Okay. So there's a reason for building those tangential beam tubes. Now, these fast neutrons are a problem. right? Because if they fly out, they go through a lot of stuff, they get into a detector out there somewhere, it will be background for an experiment, right? So very often, if one is at a reactor source especially, okay, one wants to get rid of this so-called fast neutron background. It's often one of the limiting factors, especially for low background experiments. Okay, how do you do that? Well, if you think about it, we have a certain set of materials that are good absorbers of thermal neutrons. Probably you talked about those in one of the early lectures, but if not, you can get any book on neutron scattering or any table of neutron cross sections, and you can figure out that these include cadmium, gadolinium, the right isotopes of boron and lithium, among others. There are a few other materials. We use these as shielding, but these don't help us for the fast neutrons. So if we want to shield, what we have to do is thermalize those fast neutrons. How do we do that? We have to have shielding that contains light elements like hydrogen. So when the fast neutrons hit the shielding, they thermalize, right, and then they can be absorbed. Okay? Now, unfortunately, when these neutrons are absorbed, right, they are not just benignly absorbed. They make other things, like, for example, gamma rays. Right? One thing cadmium is a strong absorber of neutrons. When it absorbs neutrons, it emits a very strong prompt gamma. Right? Wrapping your hand in cadmium to protect it from neutrons and sticking it in a neutron beam is a bad idea. You will get a very large radiation dose from the prompt gamma. Right? Unfortunately, these things like gamma also impact the detection of neutrons. Right? So if we're talking about shielding that's going to be effective, it sort of has to simultaneously thermalize the fast neutrons, right? Absorb the thermal neutrons, absorb the gamma rays. So when you walk into one of the neutron sources and you see this shielding, it's very often something that's complicated and it's composite. It might be a mixture of hydrogenous material with neutron absorbing material, and inside there might be some steel ball bearings or something to absorb the gamma rays, and there's concrete all around, which also, if it's ferritic, it might absorb gamma rays, and it also helps thermalize some of the fast neutrons. So this is actually quite a complicated business, and non-trivial. Okay, well, again, let's get back to a comparison of this fission and spallation. Okay. Fission we've talked about a little bit. Spallation, again, I'm not going to get into the full details, but typically what you're doing is you're taking a very energetic light particle, protons are what are used in most places, okay, smacking it into a heavier target. So solid targets that have been used in the past include tungsten, lead, uranium. At SNS we use mercury. The mercury is in a continuous flowing loop. This helps remove the heat. And again, this produces a highly excited nucleus. It also does some other things. The nuclei can emit energetic particles that cause further excitation of other nuclei nearby, but at the end, it turns out for each one of these protons, you make tens of neutrons. And these tens of neutrons are now, again, coming out in 4 pi directions, and they have quite an energetic spectrum. Okay, again, sort of mega electron volts. So here now is the schematic of SNS, which I'll use as an example just to describe the full process in a little more detail. SNS has a so-called front-end building. Okay, what's in the front-end building? Well, there's an ion source, and it turns out this ion source actually produces H- ions. Okay, so these are hydrogen atoms with an extra electron. And these are then accelerated by a superconducting linear accelerator, charged particle accelerator, that's about a half a kilometer long. Okay, they're accelerated up to pretty high energies, and they go through a process of stripping where 2 electrons are removed, and you end up with protons. Then they're put in a storage ring, okay, where you now have a circular accelerator that at the end of the day, produces pulses of neutrons at 60 hertz each. And these are then sent over to the target building. Now, in the target building, as I mentioned, there's an assembly that has a flowing loop of mercury. And when the protons hit that assembly, they smack into the mercury, they cause spallation, they make the 4 pi source of neutrons. And around that target, of course, we have to place moderators. Okay. So what's the net result? Well, here's the spectrum compared to a reactor spectrum. So this is here energy, and again, this is kind of on a logarithmic scale, and here's intensity. And you can sort of recognize these are the fast neutrons from a reactor, and that's the epithermal region. And the typical spectrum that comes off a typical moderator at a spallation source has a much larger component of epithermal neutrons. Okay, neutrons that are 100 millielectron volts and higher typically. Okay, so that's one difference. The other difference, of course, is for a pulse source, they're coming out in bunches. Now, the thing to keep in mind about pulse sources is in a reactor or a continuous source, right, this could be true for a continuous spallation source, we have enough time to let the neutrons actually come to sort of thermal equilibrium with a moderator, if you like. So you get out a well-defined Maxwellian spectrum. If I have a pulsed source, I cannot really do that, right? I have a reason for wanting a pulse of neutrons. So typically I have a source here which is the target that emits this spallation spectrum, and then nearby it I'll have a moderator. That moderator tends to be a lot smaller than a moderator at a reactor, which might be a fairly big volume of water. And basically this pulse of neutrons is going to pass through it on the way down the beam tube going to the experiment. So what happens is a couple things. First of all, it does not get completely moderated. Right? So there are neutrons that don't get moderated in the pulse. They just fly out at an enormously high velocity. That's the prompt pulse. And then there are the neutrons that are moderated, but they're only partially moderated. So they come out with somewhat of a different spectrum. The other thing that happens is now you have, and I'll get again to this later, short wavelength or high energy neutrons are going fast, right? The long wavelength or low energy neutrons are going slow. So this pulse is spreading out in time. And it turns out that the pulse width in time at a spallation source is generally determined for a short pulse spallation source. Let's put it that way. The pulse width is generally determined by the moderation. Certainly that is true at SNS in target station 1, which we're using now. Okay, the moderator determines both the energy distribution and the width in time of this pulse. Okay, so Jack Carpenter actually has notes in the summer school which go into great detail in all of this. And in fact, there are various tricks which I won't go into at all right now in terms of using these moderators to shape the pulse in time and shape the energy. And so you'll read about coupled poisoned moderators. Poisoned moderators means they put in a certain amount or a layer of neutron absorbing material in order to affect the pulse. Moderators can be coupled or decoupled to give sort of longer or shorter pulses, etc. Well, taking all that together, we have intense sources of neutrons. Here's a graph that has appeared many times in the literature that I will say I absolutely do not like at all, but I'm going to show it to you anyhow. That sort of shows how neutron sources have evolved as a function of time. So on the left is plotted in a logarithmic fashion thermal neutron flux in neutrons per square centimeter per second. And on this axis, horizontal axis, is plotted the year. And you can see that people started out with various different kinds of handheld sources just about and cyclotrons, and finally started building reactors, and eventually achieved high flux reactors like HIFER and ILL that have neutron fluxes of 10 to the 15th neutrons per square centimeter per second. Okay. Now there's another line on here, and this line shows pulse sources. And you can see they're going to a much higher number. What this graph fails to tell you is that the line for reactors is the time averaged flux, and the line for the spallation sources is the peak flux. Okay. These are not comparable, right? The spallation source, at least if we take SNS, it's pulsing at about 60 times a second, but with a very narrow pulse. Most of the time during that second, the flux is 0, right? So if I do the time average of these spallation sources, it actually turns out that they're significantly weaker, in fact, than the reactors. But the trick, as you will see, is that, in fact, for some experiments, it actually is this peak flux that is the important quantity, right? And that's the kind of magic of it. Now, when we look at powder diffraction, you'll really see how this works in that one case. I will warn you now that this is something that gets very, very complicated. If somebody asks you, well, what's better here, a pulse source or a continuous source or a pulsed instrument using so-called time-of-flight methods or a continuous instrument, the answer is not always obvious. It sometimes really does depend on the details. Okay, nevertheless, it means that we have a lot of scope for thinking about things. Okay, well, just to put that in perspective, Oak Ridge is one of very few places where we have in close proximity a reactor and a pulse source of neutrons. It's of both which have significant flux. In fact, right now it might be the only one where they're both operating. So it is somewhat unique. And I show here a reason why we might have both, given what I just said. So these are a comparison of neutron flux calculations for the European spallation source, okay, which is something that is hopefully going to be under construction within the next few years. And it's supposed to operate with a power of proton beam current at 5 megawatts, which compares to SNS now operates at about 1 megawatt. And this is compared with measured fluxes at ILL. Now, it's a little difficult to see this, but here you can see plots of the peak flux, and these are for various different moderators in different configurations of the ESS, which is proposed, and those are sort of these solid lines. And you compare those to ILL, and you give the fact that this is a logarithmic scale, and you can see that the peak flux gain is absolutely enormous. Okay. On the other hand, if I look at the time average flux, you'll see, especially when I go to the ILL cold source, right, which is up here, and I look at long wavelengths, and I keep in mind that this is a logarithmic scale, the time average flux is still going to be greater at the reactor if you want to use sort of thermal or cold so-called neutrons. So, the bottom line message is pulse sources in general have a big advantage if you can make effective use of the peak flux. And when you can't make more effective use of this peak flux, continuous sources win. However, that is a great oversimplification. And I will tell you that at the European spallation source, if they build it, of course, they have a plan to kind of, if you like, make the best of both worlds by, instead of having a short pulsed spallation source, building a long pulsed spallation source. But, well, my suggestion is that you go to the ESS website and read about that for yourself. It's something that will be interesting to see how it develops. Okay, are there any questions or discussion about neutron sources? Yeah, I can see that from the time we're actually running a long pulse source here as well. So we'll see how far we get today. Okay. Well, let me now talk about how we detect neutrons. Now, first thing I'm going to say is that No, detecting neutrons directly is not a good way to go. Neutrons are neutral particles. They interact, as we already discussed, very weakly with matter in general, right? So, and we don't really know very good ways of counting neutral particles, right? Detecting neutrinos also turns out to be no picnic. So the ways that we have of detecting neutrons all involve using something that absorbs neutrons in some fashion to cause an energetic nuclear reaction, which we then detect in some other way. Okay? So I show here 3 examples of these nuclear reactions to think about. Okay? First one, which is probably the most commonly used one today or to date, at least in modern neutron scattering, is using helium-3. Neutron and a helium-3 nucleus get together. You might think this makes helium-4, which is a very stable nucleus, but in fact, it produces a proton and a triton and a gamma ray, right? So 2 charged particles. Okay, that's what happens. Second thing that I'll write down here is neutrons plus lithium-6, an isotope of lithium. These actually make a helium-4 nucleus or an alpha particle, also make a triton, and also make a gamma ray. Okay. And the third thing that I'll note is neutrons plus a uranium atom. You know, that makes, well, it has a fission fragment, and it generates 160 megavolts of energy there. Okay, why did I pick these 3? Well, these are representative, but these are reactions that are used in 3 kinds of counters typically. This one is used in gas-based proportional counters. Okay. This one is typically used in a solid fashion. It is one of the reactions that is used that then has this gamma ray converted to light using a scintillator material like zinc sulfide. So this is used in a scintillation counter. And this has very often in the past been used in rather inefficient counters that we use to monitor the neutron beams. Okay, now again, if you go to a book like Beckerts and Wirtz, or you go to Jack Carpenter's notes from the summer school, you'll find a lot more detail and a lot of other things. Okay, so let's talk about proportional counters first. Basically, the simple idea of the proportional counter is this. I have a tube, inside of which is a wire, okay, outside of which is typically a metal shell, and in the center there's gas, right? And I put a high voltage drop between this wire and the outside, which is typically, you know, that's at ground, so I guess you touch it, you know, you're at ground. And what happens is the following. A neutron will come in here. A neutron will interact with a helium-3 nucleus, if you're lucky, and it'll produce this big energetic event. Okay? Now, this energetic event in the gas, which you actually use a mixture of gases, of other things like argon and methane and so on for various purposes, but what will happen is it will ultimately produce electrons. It will produce a lot of electrons. Those electrons get accelerated and produce more electrons by ionizing the gas. They get accelerated towards this anode. Okay? And there's a large multiplication of these electrons. Okay? And what this does is it gives you a voltage pulse, and I can measure that voltage pulse, and I can turn it into a count. Now, I'm oversimplifying things here, but you know, because of this fairly energetic nuclear reaction, right, this generates a lot of electrons, so I get a certain spectrum of, if you like, generated voltage that I can look at in a pulse analyzer. And if I have some other thing like a gamma ray that gets in there, it generates fewer electrons and therefore a smaller voltage drop, and I can use electronics to discriminate between them. So this kind of counter actually, although it's an indirect method of detection, as you can see, it allows one to discriminate between neutrons and, say, gamma rays. That's a fairly important thing. Okay. Now, these come in different fashions. One of the simpler things that can be done is instead of just having a conducting wire in the center, okay, if I have something that is a resistive wire, okay, what I now find is that where I generate this cascade of electrons generates a signal, it causes different amounts of charge to be deposited at one end of the wire and the other. And from the ratio of that different amount of charge, I can actually work back and figure out the position on the wire. So by making this a little differently, I can make a so-called position-sensitive detector. And these position-sensitive detectors are actually in very wide use, both at spallation sources and in some cases at reactors, commonly abbreviated PSDs. And so basically, here's a typical example of a PSD assembly. This happens to be one used at Missouri, and you can see here in this direction, the sort of position is determined by just the width of one of these tubes, right? And along this direction, it's determined by, I got 5 minutes, thank you. It's determined basically by the resolution of this whole wire setup. Okay, so we have proportional counters, they're gas-filled, we have position-sensitive detectors. Another way this can work is to have a scintillation detector. So here, as I mentioned, you're more likely to use something like lithium to produce a more energetic gamma ray. The lithium typically is going to be in a solid form, and it's mixed in some matrix where I have something like zinc sulfide. And what that does is it shifts the gamma ray from the megavolt into the volt region by converting it into visible light. And then we use standard methods. All of this stuff in here where it says photocathode, dynode, etc., just think PMT, photomultiplier tube, which you buy off the shelf. Right? So I have light, the photon is converted into an electronic signal, and this is sort of standard way that you often detect X-rays or gammas, etc. Okay, now these can also be made position sensitive in various ways. One of the more elegant ways is something that was invented by a man named Anger, and it's called an Anger camera. It's nothing to do with whether we're angry or not, in which basically one uses an array of photomultiplier tubes, okay, looking at a broad area sheet that has some kind of scintillator and some kind of neutron absorber, and now you've got effectively a position-sensitive camera. Okay, so these things are used routinely now. Typically, this kind of setup is not as insensitive to gammas as, say, helium-3 detector. So if I'm doing an experiment that has a pretty good signal of neutrons, like diffraction, not a lot of gamma interference, I might use this kind of method. If I'm doing inelastic scattering, where I really need to get as low a background as possible because the signal is weaker, discriminate against gammas, I might be more likely to use a proportional counter. Okay, if we have time, I think let me say a couple words about guides, and I'm going to save the instruments themselves for Thursday because we're running short of time. Having made these neutrons, quite often we want to transport them, and a major means of transporting them is to use what are called neutron guides. They make use of the following fact. The index of refraction for neutrons can be written in this way as a function of wavelength, and this n times b is basically a neutron scattering length and density. This index of refraction is generally less than 1. So if I am in the air and I'm bouncing off of some surface that has this index of refraction, I will get total external reflection, sort of the inverse of light coming down inside glass going to air. Okay? So what I can do is I can take a long, straight, flat, four-sided glass tube, coat it with something. The neutrons can then be, if they come in at a shallow enough angle, okay, below the critical angle, can then be guided down the tube. And it turns out the critical angle turns out to be proportional to wavelength, and you can work this out if you just use standard optical equations. You can look this up in a lot of places. The original guides were made using the isotope nickel-58 because it really has a strong scattering length for neutrons, number one, and number two, a very low incoherent cross-section. so you don't lose too many neutrons in the process. And it turns out that at 1 angstrom, the critical angle is about 2 milliradians. Okay. Why would I use these guides? Well, 2 reasons. One is to get the neutrons far away from the source and reduce background. Or I should say at least 2 reasons. Another is I can accept a larger angular divergence if I want to get more neutrons out to the sample. Now, what is more common these days are not just simple guides, but so-called super mirrors. And I think I'm going to just make a quick illustration of what a super mirror is. So basically, instead of using just one single layer of a coating of something, I imagine that I make a multi-layer, right? So now, imagine that I have a layer of A and a layer of B, right? And then a layer of A and another layer of B. Okay, what I do here is I make basically a one-dimensional crystal, and if I make these layers fairly thick, now I have neutrons that will come in off this surface and they'll Bragg scatter. Okay? And if I now plot the intensity of that Bragg scattering, I find that I get Bragg peaks. Every so often I now plot this as a function of Q. Q equals 2k sine phi by 2. What happens in a supermirror is I make this kind of multilayer, but I vary the thickness of the multilayer, which varies, if you like, the lattice constant here, and that gives me Bragg scattering at another place. So what do? I fill these in, right? And if I follow a certain recipe, I can make an effective mirror that reflects more than a mirror. That's why it's called a supermirror. And okay, if I get this back up, you can see that the spectrum of this supermirror can extend to quite large Q values or angles. Typically, things are rated in terms of the critical angle relative to nickel 58. So I have an M equals 1 supermirror, that's nickel 58. M equals 3.6, or whatever that this is plotting, is 3.6 times the critical angle of nickel 58. So this can allow us to transport neutrons of sort of broad bands of wavelengths quite far away from the source. Very useful in setting up an instrument wherever we want it to go. So I think I'm going to stop here now, having discussed a lot of sort of preliminaries, and what we will do on Thursday is we'll start getting into neutron instruments themselves in a fairly serious way. Okay, so I'm happy to take any questions or comments or brickbats, etc. Okay. You still hearing me out there in internet land? All right. Somebody's typing. All right. Any questions? Well, thank you very much, and hopefully I'll see you on Thursday, and we'll start talking then about what we actually do with all these neutrons and how we do it. And in the meantime, feel free to look up some of the information in the various sources, books, or the internet that I've given to you. And I'll come with a couple of exercises that you can work out yourself on Thursday as well. Okay, thank you very much, everybody.